Okay, everybody. Exercise G, if you have it in your manual. We're going to get a head start on tomorrow morning's exercise. Because last year we ran out of time, and then the time got shortened even more, so it'll be good. Okay, so I'll just briefly go over the first three steps, which you should have already done. Quantum GIS, again, is an open source GIS desktop system. Pretty lightweight and flexible piece of software, and if you have a basic understanding of GIS, it can be a very powerful tool for you. One of the clear advantages of it is that we're able to do this exercise. If we were all trying to use Esri ArcGIS, then we'd need like 50-some different licenses, and I don't know that Esri even works on Mac computers. So by using Quantum GIS, because it's open source, we avoid that licensing issue, and we're able to run it on multiple different operating systems. So there's some clear advantages to it. So I've just simply here navigated to the QGIS website, or www.qgis.org, and you can download the current version of the software, which is version 2.81. I looked that up on Wikipedia, and it looked like they updated the version on February 20th, so just 2 or 3 weeks ago. So I must have prepared the exercise the day before that, probably. Okay, so once you do that, you're able to install Quantum GIS, and this is the basic desktop window. You get two links. One is for the desktop, and one is for the browser, which is kind of like a Windows Explorer kind of interface to look at different geospatial layers and do various things. We won't use the browser. We'll be focusing mostly on the desktop. So if you open the desktop program on your computer, you can go to the plugins menu here. And I should say something about this. QGIS has been designed to be open source and extendable. Extendable meaning that there is a whole community of GIS people, researchers, and other folks around the world who participate in this open source Quantum GIS software development effort. And so if you go to the plugins menu and you go to manage and install plugins, it's going to try to connect here to the QGIS official plugin repository. And you get a whole suite of different plugins that can be installed and used with the GIS system. These plugins have just been developed by people all around the world who need to use GIS for some specific task and have found the default tools not as useful as they could be, and so they've set out to develop their own tool to do specific geoprocessing functions. So I have done that for the phenomics effort, creating this tool called HTP Geoprocessor. It's not going to let me, oh, there we go. There we go. So there's just my name. I'm the author. I've developed the code. I've uploaded it to the QGIS repository, and it's there, freely available for anybody who finds utility in this piece of software. Okay. So once that plugin has been installed, you'll find it under the plugins menu. Okay, what did I do? Uninstall it? This is why we need extra time. It says install, not install. Let's reinstall it. And you see a set of 4 tools which we'll be using throughout the exercise. If you take this back home and you want to use it and you have some questions on it, there is a help document. It's a PDF file that should load and just gives you a little further detail and example about the software and what it can do. So that's there for your reference after the workshop if you should need. Was everybody able to go to the fieldphonomics.org and download all of the files necessary for this exercise? Remember I asked you to do that this morning after my talk. And I realized that we're starting early, so maybe you haven't done that yet. So if you go to workshop, go to www.fieldphonomics.org, and you go to workshop, and you go to 2015 HTP workshop. Go down to, let's see, it'd be Wednesday morning, exercise G at 8:30. So the Wednesday 8:30 exercise G, that should be just the document that's in your handout book. And then there's a link for data files for exercise G. If you go there and you download those 5 files, that's what we'll be using throughout the exercise. Everybody with me? It's workshop 2015 HTP workshop, and then scroll down to the Wednesday morning 8:30 a.m. slot and click on Data Files Exercise G. Who's not with me? Is there another way? Oh, you can do this, downloads? Okay, so you can go downloads, click through there and find exercise G that way too. Okay, sounds like everybody's with me, so we'll move on. So we're on step 5, create a plot map. So it says open the file plotnodes.csv in your favorite text editor or in Excel. Let's do that. Okay, so here's the data file. Several hundred different entries in that file. This, basically, the first column is called barcode, and what that does is provide a unique identifying name for each treatment plot that is put out into the field. So in this particular experiment, we had 700 and some unique treatment plots imposed in the field. And as I mentioned in the talk this morning, then there are pairs of XY coordinates to mark the corner locations of those plots. So these are UTM coordinates. The X would be the easting value for UTM zone 12 north, where we're located now. And the Y coordinate would be the northing. These are meters. So the UTM measures in meters from some reference point. So we are 400,000 some meters east of that point, and what is it, 3.2 3.6 million, is that the right? 3.6 million meters to the north of that reference point for UTM Zone 12 North. So the biggest question last year was how you get this file. And to be truthful, we kind of generated this just based on our knowledge of our plot using some software that we have available. But you would need to generate this file on your own for your specific field. And there are multiple ways to do that. You can go out with your GPS rover and actually measure those 4 corner coordinates of your plots. Or you can actually just do calculations. If you know some reference point, the coordinate for some reference point in your field, and you know the width of the plots that you want and the length of the plots and the alleyways between, and you can go through the mathematical exercise of making the calculations for corner coordinates, knowing that from the UTM reference point, the meters number increases as you move east and increases as you move north. Now, probably one of you in here, their field is located somewhere on the boundary between 2 UTM zones. So that's a very complicated situation where you have a scene or an experimental site that actually straddles 2 different UTM zones. So that might require a little bit of special treatment. But hopefully none of you are in that category. Yep. Say again? Oh, it's just Excel's thing. If I do that, then it'll expand. Yeah, I don't like Excel sometimes for this reason. You have the option also of just using your favorite text editor. So if we open with Notepad, you will see the commas, which Excel will remove once you open it as a comma-delimited file. But you'll also see the exact decimal places represented in your data, which Excel also likes to truncate and not tell you about. Okay? So let's use that file with those plot coordinates to create a plot map or a polygon shapefile. To do that, we'll go to Plugins, HTTP Geoprocessor, and click on the Map Creator. And select then as the input coordinate file that plot node's comma-delimited file. Okay, so that's our file with our corner coordinates of our plots. And now we can specify a name for the shapefile that we will create. I think I had a suggestion. Let's call it plot polygons. Then you can click Run. Say again? Yeah, the extension for the output file, we're going to make that into a shape file. So the extension is .shp. So you can click Run. Everybody with me there? I was afraid of that. What's the trouble on Mac? Plugins? Oh, you're not. If you go to Manage and Install Plugins.
I have installed it already.
You did.
Oh,
Try it again.
Check it.
Reinstall.
I wasn't checking for it.
Oh, okay, yeah. Then try that.
I've checked it now?
No, click reinstall. Okay, you can close that now. Go to plugins. There it is. Yep. Okay, so the next concept to understand is that you have to define a coordinate reference system. So the coordinates that were present in this Excel sheet with that marked our corner points, those could be any number of coordinate systems. And the GIS doesn't know what coordinate system it is unless you tell it. For example, these points could be latitude, longitude, x, y coordinates. They could be some other planar coordinate system. So you have to actually, that's not defined here in the file, so you have to actually tell the GIS what coordinate reference system should be assigned to the coordinates in your plot nodes file. So the answer is that it is WGS 84, UTM zone 12 north. And the quickest way to get to that is to go to the filter and type in that number, 32612, and that should filter out all of the various options for coordinate systems. You find it here. Actually, once you use it one time, then it's going to appear in the recently used coordinate reference system, so we'll make use of it later, like that. Once you've done that, it will run the script, which will create the polygons from those coordinate points, and it will ask you if you want to add the shapefile to your map. You can say yes. You can exit the tool at that point. We're finished with the map creator. And there you see the plot map on your screen. So now you can do some exercises here to show you about the shapefile itself. GIS provides you with a lot of tools just natively to move around maps. You can click the magnifying glass with a plus. You can zoom in on particular plots and look at them up close. You can zoom out. If you click the, I think it's, if you can select features by going over here to this menu button, click Select Features. That allows you to highlight certain ones. You can use the Control button to highlight different ones around the field if you want to focus specifically on them. You can use this magnifying glass with the yellow piece to zoom to the selection that you have currently. You can zoom to the full layer extent using this button, zoom to layer. So you can move around the map, and the GIS provides a lot of tools natively to it to help you do that. If you want to deselect things, just make a selection outside of your map, and the selections will go away. Another important thing is that there is information behind all of these plots, and that is contained in the attribute table. You can get to that a number of ways. There's a button here which will open the attribute table for whichever layer is currently selected. You can get to the attribute table that way. You can also get to it by right-clicking on a given layer And you have some options, including opening the attribute table. So you see in the attribute table what I have is that first row, first column of information that was in this Excel sheet. So the GIS essentially used the XY coordinates here to draw out the polygons, the shape of the plot, and this barcode information was put into the attribute table for that particular plot. Then you could go in and edit this attribute table however you see fit. You can you would toggle editing, and you can add new columns and put other data into the attribute table as you see fit. Another important point is that the selections are tied between the map and the attribute table. So you can select a set of plots in the map, or in the attribute table, they'll be highlighted on the map. Likewise, you can select features on the map, and they will be highlighted in the attribute table here. Okay, so there's a direct relationship between each feature on the map and the data contained in the attribute table. Everybody with me? Yeah, a couple ways. One is you select the layer that you want the attribute table for just by clicking on the line where the layer is named, and then click attribute table button here. I will get it for you. Or you can right click on this layer and get to it from here. Okay, so let's move on now to step 6. So let's look at a crop circle sensor data file from our phenotyper here. And the file name for that is one that you download, field 119, F119, year 2012, day of year 201 at 1 p.m. And CC stands for crop circle. Here. Excel. Okay. So this file that you're seeing now in Excel would be the file that was generated by the data loggers on the tractor. So this is what would have been provided to me as a final product from the tractor in the field, and I was asked to create this geoprocessing tool to be able to do the step of taking this data and relating it to the actual treatments in the field. So you can see it's a pretty lengthy file. There are several thousand lines of information, nearly 50,000 data points or sensor readings recorded in this file. What we're showing is the latitude, longitude information, elevation as recorded by the GPS receiver. These things here are some other outputs of the GPS, including the heading, of course, it's important. And these outputs on the right are the actual sensor readings. So the first output for a crop circle would be a vegetation index, and also the second one is a different vegetation index, and then we have the R1, 2, and 3 are the raw reflectance values for a 3-band crop circle instrument. The sensor column, as I mentioned this morning, is the column that tells us which crop circle sensor is being recorded on that particular line, because we have 4 total crop circles on the tractor, and so you need an identifier to tell which crop circle instrument is being written out on a given line. Okay, so we can load that information in Quantum GIS by selecting the first step is to pre-process that information. We can't load it in Quantum yet and view it on the map. We have to first pre-process it and do the step of calculating the UTM coordinates and transforming the positions from the GPS receiver to the actual sensor. And so that tool that helps you do that is called the preprocessor. We open that. You can see all the inputs, and remember how I talked about how the purpose of this tool was to make it flexible so that you could have this tool function for many different formats that come off different phenotyping tractors or other phenotyping instruments. The purpose of this window that you see now is to provide that flexibility, but you have to specify some information to tell the GIS how to read the file that you're working with. Okay, and so you can load a file. Go down here to the bottom and say load a file that I've already created for you. It's going to be called crop circle instructions. cropcircleinstructions.csv. Open that file. That presents the information and saves the information that's needed for this particular tool to read this particular crop circle file. So you can kind of see from this the type of information that's needed and how it relates to the actual file that's recorded by the tractor. First piece of information is the total number of columns. So there's 13 columns in this file. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 total columns. So the tool is going to ignore any column that has any different number from 13. And the reason is because for this particular file, there are some places throughout here where there are lines with no data. I can find one. Probably can't find one since I want to find one. There's one. There was one. Did you see it? There it is. So just for whatever reason, the way that this file was written out, it has this characteristic that there's a missing line. And so in order to handle that case, the way that I'm handling it is to say that the user has to tell the GIS how many columns are expected, and then the software will ignore any columns or any lines that have different numbers of columns. The first column in the tool, you have to give the sensor a name. So this crop circle file records information for 4 sensors. I've got that named here, crop circle 1, 2, 3, and 4. For each of those sensors, you have to give the latitude column number. So the latitude column number is the second column. Likewise, the longitude column is the first column. And the heading column is the 7th column, 1, 2, 3, 4, 5, 6, 7. And the sensor ID column is the 8th column for this particular file. And the text associated with a given crop circle file is just simply a numeral 1, 2, 3, and 4, which you see here as the actual data recorded in the file to denote which crop circle sensor is written on a given line. The data columns are the outputs of the sensor that you wish to carry on forward in the analysis. So those are columns 9, 10, 11, 12, and 13. should be VI 1 and 2 and R1 through 3. And finally, the easting and northing offsets. So this is the way the tractor was set up in this particular season, where remember I said we assume here that the vehicle faces due north. So imagine your vehicle facing due north, and now you have to provide the easting offset and the northing offset for each of those sensors from the GPS receiver. So if for my crop circle number 1, what I'm saying is that the crop circle number 1 is positioned negative 1.524 meters east, which would be west because it's negative. It's on the western side of the GPS receiver. The second one is only half meter to the west. The third one is positive, so it's a half meter east. And the fourth one is a meter and a half east. And for the northing in this year, all of the sensors were in the same line, and they were a tenth of a meter or so to the north of the receiver. Yep. That's a good question. Let me look at my instruction file, and we'll figure out how that works. You may be right in your assumption on that. Yeah, it knows that there are two. I believe the software knows that there are 2 columns expected for the easting and northing offsets, and the number of columns fixed on the left of the file for the latitude-longitude heading. So any remaining columns in the middle, it knows are data columns. That's how I programmed it. And this piece down here in the corner, if you remember Pedro's talk this morning, we have this issue between the RTK GPS receiver that the farm uses, and this data set that we're working with was collected with Pedro's tractor, so it would have used the farm's GPS RTK system and the RTK system that's used by the USDA ALARC down the street. And that system was used to make the plot map. So we have some issue there because we've used 2 different RTK GPS receivers to make the map and to collect the data, and there's some offset between the 2. So I have included this piece down here where you can specify what those offsets should be between the 2 systems. Easy way around that, where you can just put 0 in here and ignore it, would be to use the same GPS system for both making the map and collecting the data. Okay, makes sense? So now we can go on to actually processing this piece of code, where it will go through all the different coordinate calculations and transformations of the coordinates to the sensor location. Yeah.
So when you measure the easting and northing numbers for the bottom corner, you just go to the same exact reference point?
With the 2 systems and see what their offset is.
So you do have to have a reference.
Well, no, you just have to put them at the same location. Take both systems out and put the rover receivers at the same point and let them collect some data for an hour or 2. And from there you can estimate what is the offset between the 2. So if you were doing this on your own, you have the option of saving this information. So you could click Save and name it your own instruction file, or whatever you like, and then reload that later. The Run button will actually allow you to use the information to process a file. So click Run, and then navigate to the F119 2012 day of year 201 1 p.m. crop circle file that you downloaded. And click Open, and it will start doing those calculations. And what it's going to do is create a new file where it appends pre-process to the end of whatever the file was originally named. Okay, everybody got that? Maybe if those who are ahead, if you could ask your neighbors if they're up to date and help them if they're not.
I downloaded the wrong files earlier.
Uh-huh.
So I'm trying to download these at the same time. So,
So you're having trouble downloading? Is that the deal?
yeah, that's part of it.
It's here. You go here.
Yeah, let's see. So I need to go back up here.
Well, maybe you can catch up tonight.
Sure.
And we'll start fresh in the morning. Okay, so we can then do step 7. I was going to skip that one, but since I've been given extra time, we'll go ahead and do it. So we're basically going to do the same thing for a different type of file. So I'm going to exit out of that and actually then reload it. Maybe I need a clear. I need to put a clear button in there to empty all of the entries. Okay, so now what we'll be looking at is an IRT file, which will show us that on the same phenotyper, 2 different types of sensors are recording the data differently, in a different format, which complicates post-processing, and which is why we need to have standardized procedures for representing our field phenomics data. So I've loaded into Excel now this file F Field 119, 2012, day of year 201, 1 p.m. And now this is IRT. So this is a file of infrared thermometer data. And you see clearly that the file structure is completely different than you had in the crop circle file. What we're showing here is in the first column a timestamp. I think this second column is just a record counter. The key pieces of information are here. In the third, fourth, and fifth columns, we have data associated with one IRT sensor. In the first one there, in column C, is a millivolt output. This would be whatever analog millivolt reading that sensor was outputting at that time. And the second column, I'm guessing BT stands for body temperature. This would be the actual temperature of the body of the sensor. And the third column would be the temperature of the object that the sensor is looking at. So 3 important measurements from one crop circle sensor. And we've duplicated that then 8 times in this file. There are 8 different sensors represented. So you see these same sets of 3 pieces of data 8 different times through the file. And you see here that 8 sensors are recorded across the same row and tied to, if we go way over here, latitude and longitude information and other information associated with the GPS receiver. Another important thing about this file is that I've only been given the raw output from the GPS strings, okay? And so you have to kind of study the formatting for the GPGGA and other GPS outputs, and you'll then understand what these things mean. But essentially the way that by default GPS records data is to, for example, for this latitude column, the first 2 digits represent 33 degrees. So we're 33 degrees north latitude here. The second 2 digits are now in minutes. So it's 32 degrees, 4 minutes. And then the lat-min column you see here is the decimal component of those minutes. I know that's a bit confusing. But what you end up having to do in order to make this latitude information and this longitude information make sense is split this number and then combine the 4 with this number to be 4.402366. You divide that by 60. Divide 4 by 60 because there are 60 minutes in a degree. And then add that back to the 33 degrees. After you do that, you end up with this properly formatted latitude in decimal degrees. This format here is in degree minutes. And there's other ways to represent lat-long data as degrees, minutes, seconds. So there's different formats for representing position, and you have to understand how to convert between the two. What we want for this exercise is decimal degrees. So I've made those calculations here. Another thing that was not given by default in this file, and I've had to add it later, is the heading. And I calculated that heading using a history of, it looks like, 5 previous GPS positions. So unfortunately, this is a CSV, so it doesn't show the actual equation that I used to do that. But using the history of GPS points, I've calculated this heading information here. And you can see, if I kind of scroll down, it oscillates between 270 degrees, which would be traveling west, and 90 degrees, which would be turning around and traveling back toward the east. So throughout the file, that is happening. Everybody understand that file? So now we can load the instruction file for processing that. If you go back to Quantum GIS and load the preprocessor again, so it'd be plugins, HTTP geoprocessor, preprocessor, and then hit load file again and click on the IRT instructions. Open that. So now you see an instruction file that was designed to read that IRT file that we just looked at. So here there's 40 columns of information. We have 8 total IRT sensors. The latitude and longitude and heading columns are the same for all the sensors. Here's where it kind of differs because IRT number 1 is read from columns 3, 4, and 5. IRT number 2 is read from columns 9, 10, and 11. You can see that for all the 8 different IRT sensors, there are 3 different columns from which data is read. We also don't have any inputs here for sensor ID because there is no sensor ID, because all of the sensors are written across the rows and we don't need to tell which sensor is on which row. We automatically know the order that we've programmed the sensors data to be written in the file. And again, we have the easting and northing offset sets for the sensors. The reason why we have 8 IRT sensors in this particular file is because that 4 of them were looking down at a nadir view angle. So it was pointed straight down at the crop. And 4 others were pointed at a 30-degree angle. So they were looking at an angle. So you learned some about field of view over there in the previous exercise, and you kind of know what that means. An important point on this exercise is that we're actually processing the data for those angled sensors at the position of the sensor. So it's not where the sensor is actually looking. That would require some additional processing that we haven't incorporated here. You have to be mindful of that if you choose to look at anywhere other than nadir view angles. Okay, questions here? So we can run this one like we did before and call it something, no, that's not right. Select the file. When you hit run, select the file field 119, 2012, day of year 201, 1 p.m., irt.csv. And open that one, and it will do the coordinate transformations there. Now we finally arrived at a point where we can actually load the sensor data into the GIS and lay it out on top of our plot map. So the way that we do that, and this moves on to step 8 on the 3rd page of the handout. So we want to load the data that we've processed. And maybe, since we have time, I'll show you what that looks like. So here would be the IRT data that we've processed with the pre-process extension on there. Load that in Excel. So what do you see different in this file? We see now that the IRT sensors are listed down the rows. So we have a unique row for each IRT sensor. And our latitude and longitude are blocks in groups of 8 because this is at the receiver position. Likewise, the UTM X and Y at the receiver have been calculated for that position. And they are still in groups of 8 for this case. But the UTM X and Y of the sensor are different for each of those 8. Here is the data associated with each sensor. So these are those 3 values. Be millivolts, I think that was body temperature, and canopy temperature here for each sensor, now down the rows. And then what the software does is it appends any extraneous information that was in the file to the end of this new file. So we have the different values for latitude and longitude and some other quality things and speed output by the GIS. Similarly, we can look at the crop circle file that we pre-processed. Here. And likewise, we see our crop circle data still down the rows. Latitude, longitude, heading, UTM X and Y of the receiver, UTM X and Y of the sensor, which are unique for each sensor, 5 readings from the crop circle, and any extraneous data for elevation and other GPS data that wasn't used in the previous pre-processing step. So now we can load that information into the GIS because we have these key columns here, UTM-X and UTM-Y. Because remember, our plot map was in UTM-X, was in UTM coordinates. So whenever we bring this data into the GIS, it should overlay nicely on our plot map. So the way you do that is to go to Layer. And here's where we come across the first error in the packet. You need to go to Add Layer. Go to Layer and then Add Layer. I think the Add Layer piece is missing. Once you go to Add Layer, you can find Add Delimited Text Layer. Since we're working with a comma delimited file, we want to add a delimited text layer. We need to browse now to that pre-processed file. Let's do crop circle first. So you can see that it's loaded some of the data as an example of how it's going to parse that file by commas. So everything looks fine. The key thing to do then is to specify the X field and the Y field. You don't want it to be longitude because we've converted the coordinates to UTM and we've changed the position for each sensor. So for the X field, we want to select UTM X of the sensor, and for the Y field, be UTM Y of the sensor. And we click OK. Now again, it's asking us for the coordinate reference system. So again, the text file does not have that information in it. We have to define what coordinate system our coordinates in our file are in. So remember, it is WGS 84, UTM zone 12 north. Should be in your recently used coordinate reference systems if you did the first step. Click OK. And now you see your point data loaded onto your plot map. So you should be able to zoom in and look at how nicely those points line up on your plots. The hand tool here is a pan, so you can kind of move around to different parts of the field and see how that data nicely lines up on the plots. Again, these plots are 1 meter rows. So it shows the accuracy of the GPS, able to position all of those points nicely onto your... Uh-oh, what happened there? Hold on, let me fix this, and then I'll zoom to layer. Say again? Different, okay. Like at the same point in time? So these would be in groups of 4. The tractor would have traveled over 4 rows in one direction here and then turned around. I guess I'm still not seeing what you're... Two and 3. Somebody come up here and point it out because I'm not following.
So I think what they're saying is that these two sensors seem to be closer together, the data points are closer together than the outer two. And that recurs here, these two are close together, and then these, the dots are closer together to each other than this and this. Does that make sense?
Okay.
The frequency of sampling looks higher
Or
here.
it's the frequency you're talking about.
The frequency of the sampling.
Uh-huh.
So yeah.
Yeah, that's interesting. I really don't know. Is Pedro in the room? No. The main point is that there should be 4 sets of values tied together.
Yeah, the factor is bouncing though. These might be the ones on the outside by the screen. More variation.
The only thing that you have for 4 points collected at the same time are 1 GPS location. So it could be issues with the heading, maybe error in the heading, as I think about that. That would make more sense because these two, let me do it this way. I'm gonna call it that because this would be like row 1 and this one would be row 4. These would be rows 2 and 3. So the GPS receiver would have traveled right down this line here. So there is a larger difference it would be the northing. So the northing difference between the receiver location and this line of coordinates, and similarly this line of coordinates, would be larger than between these two lines. And so I'm betting that when you do that trigonometric transformation to get those values, that the longer distance contributes to, I should say, the heading errors contribute to more error in the outer points on the boom. You guys have very good eyes, because I was like, no, that looks good, and everybody's like, no, that doesn't look very good. I don't know why. I'm betting it's due to error in the heading estimate, the estimate of heading on the vehicle, and then how those coordinates are transformed from the GPS receiver to the sensor positions. Okay, so one technical detail then is that when we loaded this file, it's still a comma delimited file as it sits right now in the GIS. And so in order to be able to do any geoprocessing on that file using the native scripts within the GIS, we have to actually convert this CSV file to a shape file. Remember I mentioned the shape file on Monday is the standard format for representing geospatial data. So we can do that. And this is part B, number 8 on number 8. What you do is you click on the layer in the layer list, then right-click on it and say Save As. Then we want to change the format of the file to an Esri shapefile. There are lots of different formats, but we're going to use a shapefile. Oops. So when we browse to our working directory, and I usually just call it the same name as the CSV file, only change the extension to a SHP for shape. You can click Save. And I've already done it, so I will replace what I've done. Say OK. So it's going to take some time because, again, there's 50,000 points in that file, and it has to create the shapefile for each one of, or create a shapefile with each one of those points in it. So it did that, and then it added that shapefile to the layer list. You see that it's basically the same. What I'm going to do now is click on the first one that we loaded, which was still the CSV file, and I'm going to remove it because we won't need it any longer. And let's change the color. Okay. So if you right-click on a layer and you go to Properties, it gives you lots of options for how you color code your information and how you want to visualize it. So this isn't on the sheet, but I'll just go through it with you since we have time. So I would select graduated color on Style, Layer Properties, Style, graduated color. And let's say we're interested in Data 1 column. Say classify that information, and let's use something other than blue because our plot map is blue. Let's use green. That'll be good because this is sort of an NDVI, so darker green should be higher NDVI and should represent more vigorous vegetative growth. Apply that. Say OK. So there you can kind of see some of the variability of the data within the plot. And we can do the same thing for the IRT file that we made. So to repeat, it would be Layer, Add Layer, Add Delimited Text Layer. Now browse to the IRT-preprocess file. There it is loaded. And now we need to specify the UTM-X and the UTM. Yeah, got deleted. Okay, let's figure that one out. Oh, you have to hit classify. Hit classify. Yeah, okay, so there's a confusing point. Back to the crop circle, if we want to change the style or something, we go to Properties. And let me slow down. Layer. Click on the layer so that it's highlighted. Then right-click. You get a list of options. Go down to Properties. And there are several things here about the layer itself. We went to Style. And there are a variety of different styles that you can choose to represent the spatial data. We want graduated. What that means is that we're going to represent the data that the data is represented as a gradation of numbers. It could be like a class. Say if you had a cultivar in a treatment plot. That's a class. So you'd want to do it based on a class of piece of classification information rather than a graduated way. I can take you through that maybe with the plot map. So then for a column, the one that we're interested in, say, is data 1. That's going to be an NDVI reflectance index for crop circle. Then, pay attention, key point, click classify. That's what people are missing. And that's going to do the classification of your data based on some settings that you have over here. And you can change the color as you like. Let's go for green because it's St. Patrick's Day and because it's vegetation. You can apply that and say, okay. Everybody with me then on the displaying of the crop circle data now? So this isn't on the sheet either, but you can do a similar thing for the plot polygons. If you right-click on Properties, and let's go Style, and in this case, let's change it to a categorized. And let's see, oh, all that's in there is barcode, so that's not going to be very interesting, but we can do it. Again, click Classify. So there's a different color now for every treatment plot. It'd be more interesting if I had actually the cultivar information in here, so then you could see the replicated cultivars across the field. If we apply that, that's like way too much color for me. So I'm going to just go back to a single symbol and have no classification. Of course, now it wants it to be green, so let's make it blue. Apply. I like that light blue color. Okay, everybody with me? Now we can do the same thing with our IRT data. So again, we would go to Layer at the top and Add Layer and Add Delimited Text Layer. Now we need to browse to that preprocessed IRT file right here. Click Open. So that will show you how it's wanting to delimit the file by commas, and that looks okay to me. Key change is to adjust the X field to the sensor UTM-X position and the Y field to the Y sensor position. Everybody there? Is CSV not default for some of you? Ah, okay. So, yeah, you have to change the file format to comma delimited. That's default for me, but maybe not for everyone. You have some options here, like this here tells you, or it allows you to specify if your first row are heading names, and it will take that into account. And some other options. We want them to be points. Are we okay now? Okay. Hit OK. Again, we have to specify our coordinate reference system, which is the same. this will ensure that the data overlies on our map nicely. And now we have another file called IRT preprocess. So, and you can see it under there in yellow. So you can turn off a layer. If you click the X, then the layer will go away. That's what the IRT file looks like, and you can see these are the pairs of IRT data. So one of the sets of 4 in this group right here would be the downward-looking nadir view, and one of them would be the 30-degree field of view. You see that the sampling rate is lower for the IRT data because you're only getting data every meter or so. Again, whichever one of these sensors is looking forward, the position of the sensor is what's being recorded here, not where the sensor is looking. You have to provide some additional offset to change that, and you could do that in the if you knew what it was, you could do that in the preprocessor here by considering additional easting or northing offsets. An issue with that, as we learned over there in the other shed, is that field of view depends on the height of the sensor. Or in other words, if you use a constant height of the sensor, then the field of view is going to change over the season as the plants grow up into the field of view. So that's why I haven't treated that piece of information here, because it's still a researchable topic. How do you handle that case where you have angled sensors? How do you geoprocess that accurately? So the first step now is to convert this IRT file to a shapefile. We do that by right-clicking again and click Save As. We want an Esri shapefile. Browse to our working directory and specify a name. Let's call it F119. SHP. Click Save. And then OK that. Okay, so that it loaded that shapefile, we can delete the first one. Remove. Okay. And we can color code our data. Again, it's I'm going too fast, I apologize. So you click on the layer and then right-click, go to Properties, and then this is again graduated data, so we'll hit Graduated. The column that we want is probably the third data column, which would be the temperature reading by the sensor. The temperature reading of the target, so temperature reading of the canopy. And so for this, let's use red. So if it's redder, it's hotter. Hit Classify. And again, here you have some options. You can pick a different number of classes. You can pick 8 classes or 9 if you wanted to. And there's different ways to classify the data. Sometimes if you pick a different classification method, it will reveal some different patterns in the data. So that's interesting. So you're seeing, like here, some effects of soil background in between the plots. They're hotter. That's what we would expect. Okay. Well, we're whipping through this exercise. Not exactly sure what we're going to do tomorrow morning now. What questions do you have? Yeah.
When you specify the EMX and the EMY options, we had options between sensor and receiver.
Mm-hmm.
When would you use the receiver for a file when you're using a file that has
So, yeah, I'll open that just so we're all on the same page. Okay, so if you remember that diagram from my talk earlier, I'll say what's here again. What's present in this file is the latitude and longitude position of the receiver, GPS receiver. Then, from those coordinates, we use an existing algorithm that's present in GIS, and you can actually download code that will do this calculation. It will automatically convert the latitude, longitude to a UTM coordinate system. So this is the UTM coordinate at the receiver, at the GPS receiver. Then we have to use the easting and northing values that we put in here that give the number of meters between the receiver and the actual sensor position. And from that, we can calculate, using trigonometric functions, we can calculate the UTM X and Y of the sensor. Just to be absolutely clear, I'll show this slide from my talk earlier this morning. This one here. So the UTM X and Y of the receiver would be at the red dot. That is where the GPS receiver is located on the vehicle. But we know that as the vehicle travels through the field, the positions of each sensor relative to the receiver change on a map, on a XY coordinate map, because you can have different headings. This is showing that, where you have a vehicle that is driving with two different headings. Well, the GPS receiver is just recording the X and Y positions, so in this case, it would be 4 and 4 for both cases. But what we are really after is the positions of the sensors. And so we have to calculate that using the known geometry of the vehicle. There's some known geometry. This would be the example of where I have you put in easting and northing in that program. The northing offset would be from here to here, that distance. It's a positive distance from 4 to, say, 6. So for this particular example here, you would put in a northing offset of 2, we'll call it meters. There's no a unit or whatever, but we'll call it 2 meters. And then the easting offsets from the receiver would be, looks like about 2.5 meters for this sensor, and 1 meter, say, for this sensor. That's negative because we put in easting, but this would be west. You look at the compass here, this would be west. So if we want easting, we have to put in a negative value to get west. negative 2.5 for that sensor for the easting offset, and negative 1 meter for that sensor. Positive looks to me like here maybe like 0.75, 0.8 meters for that sensor, and it'd be like 2.2 or so for that sensor. Now, this isn't really to scale for our real phenotyper. We have that all symmetrical, but it's just not drawn that way here on this crude example. Does that make sense of where we're getting these different numbers that you have to specify? And then again, this is the code that does it. So this is just a little script in Python that will do those calculations within the GIS software to get you to these values. From lat long, this is all we have to start with, is lat long and heading. So we want to calculate UTM X and Y of the receiver and UTM X of each sensor in relation to our plot map. I think I'll maybe stop there, and we can resume the next step tomorrow morning, where we will actually geoprocess. We'll do the step which requires that you identify which plot a given data point falls in. And with that task, you can then link your sensor data with some treatment that was imposed in this given plot where the data falls. Any further questions? Yeah? A command of what specifically? I have the code. I mean, I can give you the code. It's fairly simple code. If you're savvy with computation. It's a good point that you make, though, because thinking forward, thinking to the future, or thinking that not everyone here has a GIS technician or is GIS savvy, really what we want to move toward is some kind of data pipeline or data flow that automates all this stuff, so you don't have to have someone that sits there and does this. But we're just not, frankly, we're not there yet, and we'll get to discuss that on Thursday morning of how we can, as a community, be more closer to that goal. If we could be closer to that goal, one idea would be to have this script that does these tasks pulled out of the GIS environment that we're working and put into some other data pipeline handling program. And folks from iPlant will be here on Thursday too, and so we'll dive into that in a little more detail at that time. I'm going to wrap it up for now, and maybe Jeff has some final comments.
Just a couple of things. I guess we're going to encourage people to try and work with this this evening, because we realize this is one of those steep learning curve things. So if you got a chance to try it this evening, please do, and we'll pick up on that. Also, Andy's presentation of the little summary of results from yesterday keeps getting rolled back. We'll roll it back to tomorrow morning. And also tomorrow morning I'll clarify there was a mistake in a formula that we passed out for calculating the field of view. I tried to go around and as many people as I saw give them the correction, but we'll go over that briefly tomorrow morning.